All right. So we finished up talking about in the first lecture in this module, we discussed charges, how they come about from electrons, protons, which are negative and positive respectively. We talked about how to calculate the forces between them with Coulomb's law. Then we moved into conductors and insulators and how we can put those charges on surfaces. Now we need to talk about how like one charge setting on one side of the substance knows about the charge on the other side of the substance. Like what exactly is the way that they know each other's there? They interact with each other through forces, but the question is, how do they know when to do that, so to speak? And the way that happens is with the electric field. So electrical forces, just like gravitational forces, act between things that are not in contact with each other. So just like if you have a ball above the earth, this ball is going to be in a gravitational field. So everywhere you look, there's going to be a gravitational field. And all that means is pulling the ball down toward the earth. The ball knows that the earth is there because of the gravitational field generated by the earth. So the same idea is essentially that uh, electric charges, so electrons or protons, they also generate electric fields. And we'll see some drawings of these later. Essentially, everywhere in space, an electric field is being emitted, and that's how these particles communicate with each other. And you can think of this just as essentially as a force field. In the case of our charged particles, um, what happens is the force field influences charged particles, and then with a gravitational field, the influence is felt by massive particles or massive bodies. And the way the book describes an electric field is essentially an energetic aura that extends through space. That's fine. You can think about it however you want to. Fields can get weird sometimes, but essentially it's just the the influence of the particle spreading out in space. I guess you could say it that way. So just like in the previous slide, we were talking about the satellite. Um, you know, so we were talking about the satellite, and essentially you've got gravity pulling this satellite in, but it's in orbit, so it's going to stay there. And this is a gravitational field. So I just say grav, and then the electric field. Oops. Let me draw that correctly. So to draw this correctly, this is going to be pointing outward because from a proton, the electric field goes away from the proton, and then the electric field of the electron goes into the electron. Um, so both the satellite and the electron, so both the satellite and the electron, they are everywhere in contact with the fields that's holding them in place here. So you can think of an electric field or the force between two charged particles as essentially the force that one electrically charged body exerts on another. And basically, it's just described as this interaction between one body and the field set up by the other. Okay, so if this proton is setting up a field, then this body, this electron, is going to be interacting with that field. We could think about it the other way. Obviously, the electron also sets up a field. And that's just, we can literally just move the mathematics around and think about it in terms of the electron instead of the proton. So these electric fields, and here's a really good representation. These electric fields have both a magnitude and a direction. So your magnitude is strength, there's also a direction. So with um, this negative electron here, what you'll notice is that when you're close, the vectors or the field lines are stronger since they're longer. And as you get away from the electron, you'll see that they actually fall off and get shorter. So there is a distance thing here. And we're looking at the 1 over distance squared, so the square root law. So your electric field will get weaker as you move away from the particle making the electric field. And the magnitude of the field anywhere is simply like, if we wanted to know what the magnitude of the field was here or here or here, the magnitude is always the force per unit charge. So the force being exerted on some sort of charge. So whatever the charge, whatever the charges of the particles, that's going to determine what the size of the electric field is. So if you had a massive 1 Coulomb charge or negative 1 Coulomb charge, you'd have a really big electric field. Okay, and of course, the reason that it does decrease as you get away from it is because of Coulomb's law. So if a body with charge Q experiences a force at some point in space, then the electric field at that point is E, essentially. Okay, so here's our body of charge Q. Okay, and it's flying this way. Now, if it's negative, it's going to go against the direction of the electric field. If it's positive, let me change to a different color. If it's positive, it'll move with the field. So essentially, since this thing has a charge, we can call this our test particle. I believe the book also calls it a test particle. So there's also some charge up here. We'll call it big Q. Big Q is responsible partly for setting up the electric field. Now we have this little test particle, right? Test Q. So this is actually the charge of the test particle, the thing getting affected by the field. Okay. Let's see if I can make that smaller. There we go. So if this body of charge baby Q experiences a force at some point in space, well, we know that that force is going to be acting on the charge through the electric field, and that's how we calculate E, the electric field. So the units here would be newtons because of a force per Coulomb, and that's the electric field strength. Okay. Now, the direction of the field, like I mentioned earlier, does depend on if you have a positive charge or a negative charge. So if we think about this situation here, the direction of the field is shown by the vectors is defined to be the direction in which a small positive charge. Okay, so when we think about how things are going to flow, our test charge essentially will be positive. And we're going to think about if we just drop a little baby Q, a little test charge in here, which way is it going to move? So if we drop in baby Q here, we see that we know it's positive. So it's going to move toward the negative charge. If we drop in a positive Q here, our little test charge, we see it's going to move away from the other positive charge. So essentially, the direction of the force and the direction of the field, they're going to be they're going to point in the same direction. right? And this is just another summary to say, like, if we have positive charges, it's going to be repelled. Now, so far we've looked at just essentially electrons and protons and the fields around them, but what if we have two charges or even more charges in a situation? So the lines we've been drawing, they only show a small number of all the lines that are there to indicate the direction of the field. Okay. So for example, over here in with this proton, we could keep filling these in because there's definitely lines there. It's just you can't draw an infinite number of them. So what's going to happen is you're essentially, if you were to draw all possible options, that's just going to be a solid red circle because the field extends out everywhere. Just generally you only draw a few lines so you don't have to deal with drawing an infinite number of lines and you can still see the arrows. Now, there are lots of different configurations. Usually, well, no, that's not true. Always, lines will start from positive charges and then they end on negative charges. So there is some directionality here. And you can see that up here. So you're always going to draw from the positive to the negative. You can't have overlapping field lines, so they got to be essentially connected somewhere. And this just represents the interaction between the two particles. And then if you have something beyond just a set of 2-point particles, you can also have charged plates, and we'll talk about this a little later, like metal plates. And essentially what happens is, in this situation, when you have a nice flat big surface, your electric field lines just shoot straight across. But they're always going from the positive to the negative. And this is essentially going to show you how a particle will move in the field. Like if we put in a little baby Q, you see it's going to be repelled, but at the same time, this negative charge over here is going to be pulling it over. Down here in these photographs, A, B, C, and D, so these are actually real photographs of some charged threads. They're following the lines exactly. So what you see here is you see looks like a positive charge and a negative charge since they're connected. And you can see all those field lines everywhere. And then over here, looks like we have a positive charge and another positive charge, or double negatives, because you can see these field lines, they don't want to interact with each other because they're the same charge. So you can see that they're actually turning, moving away. Here you can see we've got two charged plates. So could be this one's positive, this one's negative. The threads in the picture don't have arrows, so it's hard to tell which way things are flowing. But you can see here that they're straight across. Oops, I drew that the wrong way. It's got to come from the positive, so it comes down. Okay. So the whole point here is that when charges move, their motion's communicated to other charged bodies in the form of a field disturbance. So again, this is how these particles are communicating. What's really neat is this idea of electrical shielding. And essentially, this is how you can cancel out an electric field if you don't want one. So electric fields can be shielded by lots of different materials as long as they're metal and conducting. The amount of shielding depends on the material being used as a shield. And we'll talk about exactly how this works in a second. So the electric field inside a metal is 0, regardless of what the field strength is outside. So if you had some sort of metal housing, your electric field inside will always be 0. And the reason that happens, we can think about this in terms of these charges over here in this diagram. So on a sphere, the distribution of charges over the surface will be uniform. That makes sense. Spheres are very symmetrical. There's lots of symmetry going on. So we always get a uniform distribution. So the whole idea here is everything gets spread out evenly because there's nice, pretty symmetry. Okay. Um, that's not the case with non-spherical conductors. So if we had a square, you might say, yeah, a square is symmetrical and everything. But if you think about it, if we draw a line this way versus draw a line this way, it's not the same, right? There's no the symmetry is very different. However, if you have a circle, no matter how you draw a line through it, the symmetry is always the same. See, hopefully my eraser works. Sometimes it doesn't. Oh, good. Okay. So you can see this whole idea of a uniform distribution of charges doesn't always work because we have a bigger distribution on the corners than we do on the long straight edges, right? There's only like, it looks like two protons chilling there on the edge versus a clump in each corner. And same thing down here with this egg shape. You can see there's a bigger, thicker distribution of charges down here versus spread out along the top, which means you're just going to have a non-uniform distribution of charges. However, what's interesting is the electric field inside any conductor will always be zero anywhere inside the conductor. So even though you have this really weird distribution, if these are conductors, even though you have a non-uniform distribution, your electric field inside is still zero. And the way you can think about this is essentially electrons will always distribute themselves across a conductor to be in equilibrium. They want the electric field to be zero, right? Because if the electric field does not equal zero, things should be moving. Should be moving. Well, these particles, these charges don't want to keep moving around, right? So they're going to figure out a way to distribute themselves to cancel out the electric field. They're lazy. They don't want to move. So they're going to get rid of the electric field to keep from moving around. So that's why on the surface of a conductor, they will find that one distribution to keep things to keep things in equilibrium, to keep the electric field equal zero. Okay, now we can talk about how to actually apply that. To shield an electric field, um, we need to surround the object that we want to shield with some sort of metal. Okay, so here's my object. We'll wrap it in tinfoil or something. Okay, so we'll place the shielded object in an electric field of any strength. So that means if we have some electric field coming this way, it actually doesn't matter because our object in here is shielded. What's going to happen is that free charges on the shielding material, so all these, I don't know, let's say that it's negatively charged, all these charges will rearrange themselves to cancel out all field contributions. So these charges, the electrons, they will cancel all of the fields. And that's even the external one. Right? And that'd be this field over here. So the whole idea here is that these electrons or protons or positive charges, I guess I should say, they are all so lazy that they want to cancel out even external fields to keep from moving. And that's how the basics of this shielding works. And you've probably seen some of these electrical shields. This material here in the picture, if you've ever like stripped a wire to like, solder it onto something else, essentially a lot of your everyday electrical appliances, they have this metal shielding sheath wrapped around all the wires inside. That's exactly what it's there for. It's there to shield those internal wires from any sort of external electric fields. Okay. Last thing, electric potential. So that's our electric field, how the particles communicate over space. Well, let's talk about how we can actually store energy in that space. So an object held above Earth has a gravitational potential energy, right? We remember that. Just like a gravitational potential energy, a charged object also has a potential energy. And it's also set by location. So you'll remember that if you have the Earth and a ball, increasing the height above the Earth of the ball will increase your gravitational potential energy. So it's position dependent. And it turns out that the charged objects, if they have a potential energy inside an electric field, it's also position dependent. Now, if you think about it, if we were to compress a spring, that requires work, right? So we're applying a force over a distance. That's our definition of work. So we take that work and we turn it into potential energy. So that's going to be work to potential energy, because that spring now has the energy to do something, right? It wants to jump back to its original position. So we've got some potential energy stored in the spring. Same idea here. Just as work is required to lift a massive object against the gravitational field, just like work is required to compress a spring, work is required to push a charged particle against the electric field of a charged body. Okay, so just like the spring up here, we have some nice distance here between this proton and this charged sphere. Now, if we apply a force, that's going to be, we're going to have to do work because it's a force over a distance. You can see we changed that distance, call it distance x. We compressed, or we didn't compress, but we pushed this particle in. It wants to repel, but we pushed it in, so we had to do work. Okay, now this work being done changes the electric potential energy of the charged particles. Okay, so this proton over here has a different electric potential energy. Now, rather than dealing with the potential energy of a charged particle in an electric field, because in this case, we have to know what its charge is to talk about its electric potential energy. What we can do is we can set up the math to kind of ignore the charge on the particle, right? Because we don't want to have to, we want information about the field. You want to know about the field. Oops, there's an L. You want to know about the field, not necessarily the information about the charge of the particle. So what we can do, we can set up the math to ignore the charge of the particle, but still get the information about the field. And then all I'm saying pretty much is essentially the charge on the particle is divided out, okay? So we can have this electric potential energy, but then if we just divide that by this obnoxious charge, right? We don't care if it's positive or negative. We just want to know what the field is, or the potential in the field is. So we can divide out the charge. Let's see, divide out the charge. And it turns out, so this is going to be essentially the energy, how much energy the field has to give per any charge that might be in the field. So it's a density. If you think about like, if you get, you know, I don't know, 10 joules of energy per candy bar or something like that, you're still thinking about the amount of energy, the 10 joules of energy. You're not thinking about how many candy bars you've eaten You're just thinking about how much they're going to give you. So this is a density. And that's all we're going to do. Instead of talking about an exact number, an exact amount of charge in this field, we're not going to say like, oh, this charge of 2 coulombs gets whatever. No, we're just saying for whatever amount of charge is there, we don't care. This amount of charge is going to get 10 joules of energy or whatever. So the idea of this whole energy density type thing, the unit of measure for this electric potential is the volt. And I'm sure that most of you have heard people talk about volts or voltage. And usually it is referred to as voltage. So the electric potential and voltage, these things are equivalent. The voltage is essentially a potential energy or a measure of potential energy. So we'll say a measure. Or an energy density. Okay, so we can think about one simple example here. We have same equation, electric potential equals the potential energy divided by how much charge this might be applied to. So in the most basic case, if we have 1 joule of energy applied to 1 coulomb, well, that's the definition of a volt. A volt is 1 joule per coulomb. So if you have 1 coulomb of charge in an electric field, 1 volt means it's going to get, there we go. Oh, that's weird. Let's see. Let's do it this way. 1 volt means it's going to get 1 joule of energy. Okay, that's the definition of 1 volt. Oh, yep, we already said that. Great. And then if you think about it, we can actually do a quick numerical example here. So if you rub a balloon on your hair, the balloon becomes electrically charged. You've seen this before. What's interesting is you can actually charge up a balloon to like many thousands of volts. So even like, 100 kilovolts or something. But the voltage is actually high because the net charge is tiny. And net charge is important here. So if you think about it, if you do 0.1 joules of work to charge up a balloon, okay, that 0.1 joules of work may only give 1 millionth of a coulomb of charge to the balloon. So if we're going to do 1 joule, nope, 0.1 joule of work to this really tiny 1 times 10 to the negative 6. If it takes just a little bit of work to give this thing a small charge, let's think about this. So we know the electric potential energy, because we had to do work, that work is converted to electric potential energy. So we convert our 1/10 of a joule to energy. That's 0.1 J for joules. And then it's joules per coulomb, right? 1 millionth, very tiny, of a charge gets applied. So if you do the math and do the division, you actually do get 100,000 volts. So the whole point here is that when you do a lot of work on just a little bit of charge, then you get a really big voltage. Now the question is, where can we store this? The answer is we can store this in energy in the electric field. Okay, and we can generate, we can hold this electric field in something called a capacitor. So electric energy can be stored in a common device called a capacitor. And basically, oh, and by the way, a capacitor storage potential is measured in capacitance or farads. So a big capacitance means it can hold a lot of energy. Big capacitance means lots of room. Lots of room for energy. Doesn't mean there's actually physical space. It just means there's a big potential to hold energy there. So the simplest capacitor is basically just a pair of conducting plates separated by a small distance. And you can see that here. Here we got a positive plate, negative plate connected to a battery, and they are separated by some distance. So if you connect these plates to a charging device like a battery, electrons are transferred from one plate to another. So essentially, your positive terminal and your plate will become positive. Your other plate will become negative when it's connected to the negative terminal. So now you'll notice that you've got all positive charges on one side, all negative charges on the other. And we know what that's going to look like with the field. We're going to set up a electric field in here. It's going to go from the positive plate to the negative plate. Okay. When you do this, if everything's working as it should, the charging process is actually very fast. So you can actually store energy into a capacitor very, very quickly. As fast as if the plates in the battery, if the voltage between the plates is the same as the voltage between the battery. And when that happens, you get really quick charging. Again, the greater the voltage, the larger and closer together the plates are, the more energy you're going to be able to store. And in everyday devices, you'll find if you crack open, I don't know, like an old VCR or an old DVD player that's sort of broken, you'll find lots of these capacitors, and they look like this. Essentially, in here, you're going to have two metal plates, and these two plates are going to have different charges on them. And then you're going to store, store electrical energy in them. Man, I can't write today. Energy, there we go. You can actually use something called a dielectric, which just could be a metal. No. It could be an insulator or it could be paper. But you can actually put a dielectric in here. And that'll actually change the capacitance and either increase it, decrease it, whatever you want to do. It just depends. Some capacitors even use like some oils, but you can actually sort of cheat and game the system by introducing a dielectric, and that'll change your capacitance. But some places you'll actually see this is like a camera flash. Or a defibrillator. I'm just going to write defib because I don't know how to spell defibrillator. Anything where you have to discharge very quickly. So a capacitor really is a fast battery. Instead of releasing energy slowly, you want to dump it. Okay. So we'll say quick charging. And quick discharging. So think bright camera flash or defibrillator, anything you want to just dump a big current all at once. And speaking of current, we've pretty much hit everything we need to talk about for electrostatic. So this is electricity not necessarily moving. In the next module, we'll actually talk about current, which is the flow of these electrons. And then we can start talking about circuits and how some of these everyday devices work. So until then, feel free to email me with questions. And I look forward to getting started on electric current next time.